Yes, hello students. Now we are going to start the second part of unit number 2, that is chopper controlled DC drive. In rectifier control, the source was AC and we used a rectifier there in between source and motor. Now in this case, we have the source is DC and we have to use some DC to DC converter or DC chopper in between motor and the source. So there are two possible ways in this. Uh, One is the motoring mode, that is when the power flows or energy flows from source to motor and the machine operates in the motoring mode. And the other way is the energy flows back from motor to source side, that is generating mode. So today I will discuss the motoring mode and the circuit that is used for this motoring mode operation. I will discuss and briefly explain its operation. So you can see here, this is a diagram, simple diagram for a chopper controlled DC drive, where this is the DC voltage source. It can be some battery or some PV panel, or it can be some voltage source coming out from some rectifier. So it is a DC voltage source, and we are using here a switch, that is I have shown it by the symbol S and by this arrow. This is this should be a fully controlled power electronic switch like MOSFET, BJT or IGBT. Usually thyristors are not used in the case of chopper because thyristors are latching devices. When they are turned on, they can be turned off only when the current falls below zero, and this doesn't happen naturally in the case of DC supply. So we use some device that can be that's turned on and turned off, both can be controlled. So MOSFET or BJT or IGBT, they are getting some gating signal. When the signal is available, they will remain on. When the signal is removed, the switch will turn off. So it is fully controlled switch of usually thyristor family, that is MOSFET, BJT or IGBT. So these switches can operate at high frequency also as compared to thyristor. So there are advantages of these transistor switches. So and here we are connecting a diode that will work as a freewheeling diode in this case. So simple operation is that you have to give signal to this for some time period and then remove the signal for the remaining period of the cycle, and the switch will turn on and turn off automatically. So this is the signal that you give to the gating signal. It can be a base current in the case of BJT, it can be some voltage signal for the case of MOSFET. So this gating signal is there. It will be given for time period T on and it will be removed for the time period T off. The whole cycle that you may call as the time period of operation T. So this is the time period of operation, and the reverse of it you can call as frequency of operation of the chopper, and that is kept very high in several kilohertz, and I will discuss it later what is the advantage of high frequency operation. So the voltage, the switch is operated at a very high frequency, some kilohertz, and of course the voltage that appears here will vary. Briefly you can understand that when we give the signal, the switch turns on, the voltage is connected across the motor, and the source voltage appears across armature, and when the switch is turned off, then current flows through the freewheeling diode, and the voltage across the motor becomes equal to 0. So you can say that during the on period of the switch, the voltage across armature is equal to the source voltage V, and when the switch is turned off, current is forced to flow through this diode, freewheeling diode D, and the voltage across armature will be same as the voltage across the diode, and if we are assuming ideal switch here, the voltage will be equal to 0. So in that way the voltage will fluctuate across the armature. And as I have said earlier, this is done at a very high frequency, and motor is being a mechanical device having a large mechanical time constant. It will not respond to this quickly changing voltage. It will rather respond to the average value of this voltage that I have shown here, V average. So it will respond to the average value of the voltage and attain certain speed corresponding to this voltage. You know that the speed of the motor depends on average value of the voltage across it. So the motor will achieve certain speed depending on the value of V average, and this V average also of course depends on the ratio of on period and off period of the switch. So depending on that, it will attain certain average value of some speed, and motor will have the back EMF equal to K times that speed, Q omega M. So you can say that the motor will run at a steady speed, and corresponding back EMF, you may call it E, that is equal to K omega M. Omega M is the speed corresponding to this average value of the voltage. Now here let us define one term, that is duty ratio. Duty ratio means the ratio of the on period, that is the duty period where the power is flowing into the motor, divided by the time period of operation. So this we denote by delta and we call it duty ratio. Now let us briefly explain understand the operation of this circuit during the two intervals, that is the duty interval and during the off duty interval, or you may call it as freewheeling interval. So what happens during the duty interval, that is time is between 0 and t on. Now you must understand that I am explaining the things for steady state condition. In the first cycle, when you just start, switch on the supply here, in that case the motor speed is 0, the motor speed will rise only gradually. So in the first cycle, of course, the current will start from 0, it will reach certain value, and then it will start decreasing, rise, and finally in steady state condition, current will fluctuate between two fixed values. So I am explaining the things which in the steady state condition. So during the duty interval, you can say that this diode D will be in the switch is connected here. This voltage will appear across the diode D, and diode D will be in the reverse bias state. So it will be out of circuit. The circuit will be completed like this, between start from voltage and this motor like this. So you can draw the equivalent circuit of this in this way. During the duty interval, voltage is connected across the motor. The motor I have shown by its equivalent circuit, that is the resistance of the armature, inductance of the armature, and the back EMF, as that will be, you can treat it as a constant voltage source. This E will be equal to K omega M, that is the speed corresponding to the average voltage here. So this is V equal to, apply KVL here, Kirchhoff's voltage law here. So V will be equal to RAIA plus LA DIO or DT plus the back EMF. So this is the KVL equation, and you can bring this term on the left hand side and write the equation like this: V minus E equal to RAIA plus LA DIA or DT. So this equation you may call as equation number 1. Now how to solve this problem, this equation? You want to know what is the expression of the current IA. So IA can be written in this situation. You can write the steady state solution and the transient solution. In the steady state, the current will be equal to V minus E upon RA, voltage source, divided by the resistance. You know that in the RL circuit, the steady state current is equal to V upon the resistance. So here it is the voltage. You can say that this is the voltage source of magnitude V minus E. So you can combine these two sources together. So it will be V minus E divided by RA, that will be steady state current, and this is the transient current having the term some constant K1 e to the power minus t upon tau a. So this equation you may call equation number 2. Now you must know the value of k1 to write this equation. So k1 can be obtained from any boundary condition. As I said here also, that the current will in steady state fluctuate between two fixed values, minimum value and maximum value. So minimum value I am calling IA1, maximum value I am calling IA2. So from the boundary condition you can say that at t equal to 0, current is equal to the minimum value IA1. So let us put the value here and you will get constant K1 equal to IA1. So when t equal to this term will be equal to 1. So K1 will be equal to IA1 minus B minus E upon RA, equation 3. Putting this in equation 2, you can write the final equation for the current. I equal to V minus E upon RA, 1 minus e to the power minus t upon tau A plus IA1 e to the power minus t upon tau A. Tau A is nothing but the time constant of the RL circuit, that is LA upon RA. So this is the equation of the armature current. But here one thing is not known. What is the value of IA1? This IA1 is still not known to you. What is the value of this IA1? That we have to find out. Then only you can write the complete equation of the armature current. At the end of duty interval, that is t equal to tau A and delta t, you can see that the current will be equal to IA2. So IA2 will be equal to V minus E upon, just put t equal to delta t here, and this is the equation for the current IA2. So this IA2 is known in terms of IA1. Later on, when we do the analysis for the free-wheeling interval, we can find out another equation, and that can be solved to find the values of IA1 and IA2. So let us first understand this completely. That is, during this interval, current rises, and you can see here the equation of the current is having some exponential term. So actually, if you draw the current waveform, that is, suppose you don't turn the switch off, keep it on for long enough time, what will happen? Current will start from say I1 and then it will rise, finally reach the steady state value, that is V minus E upon RA. So this is exponential rise. But as I have said that we have to keep the frequency very high, and the time period, the on period is much smaller than the time constant of the circuit. In that case, it is only a small part of this rise. So initial part is always linear, later on it becomes non-linear. So that is why I have shown here only it like a straight line, because it is a small part of the whole, you can say, that time period, or you can say the time constant. So this can be said to be linear. So during this interval, what happens? The diode is not in picture, diode is in the off state, and the current rises from IA1 to certain value IA2 when we remove the signal from the switch S. So as it is fully controlled device, as soon as we remove the signal, it will go in the off state or the blocking state. So current cannot flow through this switch now. So earlier the current was flowing through this circuit, and this was the situation. That is, the polarity of the voltages across resistance, inductance, current was rising. So dIA or dt was positive. So this voltage was also positive, and energy flow was somewhat like this. The energy is coming from the source. A part of the energy is dissipated as heat in the armature resistance. A part of this will be stored in the inductance, and the remaining part will be converted into mechanical energy. So the energy is flowing from motor to source, the source to motor. A part is dissipated as heat, a part is stored, and a part is converted into mechanical energy. So now this energy is available here in the case of in inductance, and when we interrupt the switch, when we close the switch, then what happens? When we open the switch, what will happen? Current will start decreasing. So earlier current was rising, when we don't connect the voltage here, current will obviously go down. So what will happen actually? Then in that case, the polarity of inductor voltage will become uh, opposite to what it was earlier, and you can see the diode was connected here, which was in the off state when the switch was uh, closed. But when as soon as switch is opened, what happens is that current starts, instead of rising, it will start decreasing. That will cause the polarity of inductor voltage to reverse. It will become opposite to what it was earlier. So this voltage will rise and it will become so high that it will make the diode turn on in the on state. Even though this back EMF will try to reverse bias the diode D, but because of this inductor voltage, it will overcome this back EMF and will make the diode in the forward bias state, and current will start flowing through this diode. It will start freewheeling through this diode. Freewheeling means there is no opposition here, source is not connected here, and the current will start decreasing. Energy stored in the inductance will start dissipating, and this energy will be converted into mechanical energy by the motor, and remaining will be dissipated as heat in the armature circuit resistance. So during this interval, the current will start decreasing, and if you don't close the switch again, the current will finally reach the value equal to 0. But before the current reaches 0, we again turn on the switch and the cycle will repeat. Again the current will start increasing. So this is the whole operation. I have shown here the source current also here. You can say that when the switch is closed, current flows through the switch, and when the switch is turned off, the armature current flows through the diode. So you can say that the source current will be like this. This part of the current flows through the source. So this is the waveform, the source current like this. So this I think I have drawn by mistake here like this. So this is the source current. Similarly, the diode current will flow only when in the switch in the off state. That is during the off period of the switch, the current will flow like this. So this is the waveform of the diode current. So now we have to do the analysis for the off freewheeling interval, so that we can solve for the values of IA1 and IA2, so that we can write the final equation of the current IA. So I will just do the analysis of the freewheeling interval. Now let us discuss the operation during freewheeling interval. So during freewheeling interval, as I said earlier, the switch is turned off and the diode D starts conducting, and the current starts flowing like this in this circuit. And as we had shown earlier also, the polarity of inductor voltage during this period will be like this. So energy will be released by the inductor, and it will be partially converted into mechanical energy, and partially it will be dissipated as heat in armature circuit resistance. So during this interval, if you write the KVL equation, voltage is 0 is equal to RAIA plus LA over dt plus the back EMF E. You can take E on the left hand side and write it as minus E is equal to RAIA plus LA over dt. Now you have to solve this equation again. You treat this as a voltage source. So this is simply RL circuit where the voltage source is equal to minus E. So the solution of this equation, IA will be equal to steady state term, voltage upon the resistance, plus the transient term K2 e to the minus T dash upon tau A. So T dash I am taken from this interval, that is from this point of time. So T dash you can write as T minus T on. that is t minus delta t. So t dash is the reference of t dash is from this point. So at this point t dash is equal to 0. So now this is the, now you can see that when t dash is equal to 0, that is beginning of the freewheeling interval, the current is at its peak value, that is equal to Ia2. So using that boundary condition, you can find out the value of the constant K2. Here put I equal to Ia2 and t dash equal to 0. So you will get the unknown constant K2 in terms of Ia2 and E. So this is question number 8. Now you put this in the question number 7 to write the final solution. I equal to minus E upon Ra, 1 minus e to the power minus t dash upon tau A plus Ia2 e to the power minus t dash upon tau A. This is equation number 9. Now again here the value of Ia2 is not known to you. From the previous equation you got one relation between Ia1 and Ia2. So at the end of this cycle, that is at the end of freewheeling interval, that is at t equal to capital T, or t dash is equal to t minus delta t, that is 1 minus delta t. So at this time, instant of time, current will be equal to the minimum value, that is equal to Ia1. So you put this value of t here. So you get the equation Ia equal to Ia1 minus E upon Ra, 1 minus e to the power minus 1 minus delta t upon tau A plus Ia2 e to the power minus 1 minus delta t upon tau A. Equation number 10. Now this is another relation between Ia1 and Ia2. We have already one equation, equation number 5, that relates Ia1 and Ia2. So there are two equations and there are two unknowns. You can solve it to find the expression for Ia1 and Ia2 like this. Ia1 will be equal to B upon Ra, e to the power delta t upon tau A minus 1 upon e to the power t upon tau A minus 1 minus E upon Ra, equation number 11. And similarly Ia2 will be equal to V upon Ra, 1 minus e to the power minus delta t upon tau A upon 1 minus e to the power minus t upon tau A minus E upon Ra, equation number 12. Now knowing these two equations, you can find out the current ripple. That is, current actually will have certain average value here. This average value will be equal to actually Ia1 plus Ia2 divided by 2. So this is average value, and the current ripple that you can show here can be shown like this. So this is the current ripple. How much current is above the average value of the current? So that you can define as Ia2 minus I1 divided by 2. So this is the current ripples. And as you know that for good operation of DC motor, current ripples should be as low as possible. For normal operation, when we feed the DC motor from some DC supply, current is DC, continuous current is there, no ripples are there. So here also current should be as smooth as possible. So you can write the expression of this. So just put the values of I1 and Ia2, you get this expression. 1 plus e to the power t upon tau A minus e to the power delta t upon tau A minus e to the power minus 1 minus delta t upon tau A. It is not very clear. It is 1 minus e delta t upon tau A upon e to the power t upon tau A minus 1. So this is the expression for the current ripple. Now we have to see what is the maximum value of this current ripple. If you want to find it out, you just differentiate it and equate it to 0. You will find that this will happen when delta equal to 0.5. So when duty ratio is 0.5, in that case the current ripples will be maximum. So that maximum ripples comes out to be V upon 2Ra e to the power 0.5 t upon tau A minus 1 upon e to the power 0.5 t upon tau A plus 1. So this is the expression for maximum ripple. Now you can see it is obvious from this equation that the ripples will increase when the time period t increases. So this means that you want to reduce the ripples, then you have to decrease the time period of operation. That is, you have to increase the frequency of operation. So higher the frequency of operation, lesser will be the ripples in the armature current. And similarly, the ripples will decrease when the you can say the time constant of the circuit is increased, and that will happen when inductance is higher. So it is quite obvious. When inductance is higher, inductance opposes the rise of current or change of current, so the ripples will be less. So if you want to minimize the ripples, you have to increase the inductance of the armature circuit, and you have to increase the frequency of operation of the chopper. So that is why the chopper is always operated at a high frequency, so that the current ripples are minimized and the motor behaves as if it is fed from a normal DC supply. The losses in the machine will reduce and the performance of the machine will improve if we increase the frequency of operation. So this is the operation of chopper controlled DC drive for motoring mode. Now you can see here that in this case energy can never flow back to the source. So it is not possible to have regenerative operation in the case of chopper circuit that we have discussed here. For braking operation or the regenerative operation, you have to use some other circuit. So that circuit we shall discuss in the next lecture. Thank you for today.